Hi there. My name is Jeremy, and today I'll be talking about Metropolis Markov chain Monte Carlo algorithms for a Bayesian regression. So briefly, I want to talk about why we use MCMCs, and in particular, this is tied to Bayesian modeling. Now, Bayesian modeling has been around for quite some time, but it wasn't until MCMCs came out that it really expanded how complex of Bayesian models that we could actually fit. Next, I want to talk about what an MCMC is, and in particular, I'll focus on the Metropolis Hastings algorithm. And we'll talk about this pretty briefly, but there are many different MCMCs out there. And then the focus of the workshop is on how to actually implement one of these MCMCs. Now, to begin, let's think about what one of our ultimate goals of whenever we're conducting some sort of quantitative analysis. Generally speaking, we are estimating parameters and drawing inferences from a sample that we've collected from the population. So this might be looking at the probability of some sort of mean difference in the population after we've gotten a sample of data from that population. And with the Bayesian approaches, we do this by calculating the probability of the parameter value. So in my example, the mean difference in the population, given that given some sort of data. So for example, the mean difference in the sample. And we might be interested in looking at a lot of different variables. Acceptance and commitment therapy was a really popular type of therapy where I went to grad school for reducing anxiety. And so we might be looking at whether that form of therapy is effective in the population based off of how well it does in our samples. Now, to calculate the probability of a parameter value given our data, we use Bayes' rule. And when I referred to this before, I described it as the probability of our parameter given the data. Generally speaking, however, we're actually describing a probability distribution. So it's not just one parameter value given our data, it's actually a range of parameter values given our data. And so on the left-hand side, which is our ultimate goal of what we want to try to get with a Bayesian analysis, this is called our posterior distribution, sometimes just shortened to posterior. On the right-hand side, we have our joint distribution divided by our marginal distribution. So in the numerator, that's our joint distribution. We have the likelihood on the left-hand side. This is the probability of our data given a parameter value, although, like I said before, this is typically represented across a wide range of parameter values. On the right-hand side of the numerator, we have our prior probability of the parameter. That is the probability of the parameter before we've seen any data. Now, that doesn't mean that we do not, we have to set our prior probabilities well before we collect our data. This is just the probability of the parameter without considering the data. That might be a better way to put it. And then the denominator is referred to as the marginal distribution, sometimes referred to as the evidence or the probability of the data. And as we'll see in a bit, we actually won't have to deal with the marginal distribution a whole lot. So I'm not going to discuss that in too much detail. What I do want to talk a little bit more about, because this is a source of controversy, and sometimes enthusiasm is the prior in Bayesian modeling. Now, as a source of controversy, some individuals have likened using informative priors to data fabrication. And effectively, this argument rests on the fact that mathematically speaking, whenever we use very informative priors, it functions very similarly, and in some cases, functionally equivalent to inserting more data into our sample. Then we've essentially fabricated some extra data. On the other hand, however, priors are useful in a few different ways, besides, for example, setting really informative ones and conducting basically core science. And I think it's helpful to illustrate some of the usefulness of priors with an example. So again, remember the prior is the probability of the parameter before you see the data. And we very frequently represent the priors as a distribution. And this is very practical because we would not want to set the prior probability for every single possible parameter value that we might be interested in looking at in our analysis. It's much easier to just describe it as a probability distribution. And really what we're doing with a prior is we're asking the question, what are some plausible values of this parameter? And that's a pretty reasonable question. Let's take, for example, IQ scores. So we know that with IQ scores, they're normally distributed with a mean of 100 and a standard deviation of 15. And now, if we didn't want to make any prior assumptions is not the right word. If we didn't want to, I guess, think about any plausible values of, let's say, estimating the mean of a group of individuals' IQ scores, we could set a uniform prior. Now, this is perfectly fine. This is essentially what occurs in frequentist approaches, but it's important to consider the implications of what we're actually doing here and what we're assuming. We're assuming that, let's say, an IQ score of 55 is equally likely as an IQ score of 100. And here I've displayed my uniform prior in the blue line here. But again, we know something about IQ scores. So we know that a uniform prior really doesn't make a whole lot of sense for our data. That we do actually know at least a little bit about how IQ scores work. And although 55 is a plausible value, it is an unlikely value, at least relative to an IQ score of 100. And we can incorporate even just a little bit of this idea that an IQ score of 100 is at least a little bit more probable than an IQ score of 55 by just setting a weakly informative prior. So here in yellow, I have a normal prior with a mean of 100 and a standard deviation of 40. Now, this is considered a pretty weak prior because the standard deviation is pretty large. And if you compare these, really, I'm not saying that 100 is drastically more likely than an IQ score of 55, but I am saying that it is more likely, which seems to reflect how IQ scores actually function. And now, well, this is a nice aspect of including priors in our data analytic approaches. There is actually a very practical benefit to using somewhat informative priors. Maybe not very highly informative, but at least weakly informative priors. And that's it can, I should say, improve estimation. That whenever we build our MCMCs, we can help the MCs not get stuck in an unlikely parameter space by using priors. So for example, if we have an MCMC, the MCMC is going to sample from this wide range of values, and it could possibly get stuck in, let's say, the IQ score of 60 and think that that's where our group's mean is. And even though that's a very unlikely parameter space, but if we use a more informative prior, like I said, even just a weakly informative prior, this can actually help improve our ability to estimate our parameters, because here we're saying, okay, those values are a little bit less likely, so let's get out of that parameter space. So we can kind of help our MCMCs move out of those unlikely areas of our probability distributions. And then we can also actually incorporate some conservatism in our analyses using priors. So for example, let's consider a beta coefficient for a regression model. So when a beta coefficient is equal to 0, this means that there is no effect of whatever independent variable that you're looking at, whether it's age or uh, let's say smoking status, for example. A value of 0 means that there's no difference between, or no effect of that independent variable. Now, if we set a uniform prior, we're saying that this effect could have any range of values. It could be extraordinarily high. However, if we use a little bit more of a conservative approach and we say, look, we want to test this effect. However, we do want to center it around 0. If we use a more and more informative prior, so let's say a normal distribution with a mean of 0 and a standard deviation of 1, that's a relatively informative prior, particularly for a beta distribution, or not beta distribution, beta coefficient, I suppose, depending on the variability in the data. But what that's going to do is it's going to draw our estimate just slightly closer to that 0 value. And this can help us incorporate conservatism in our models so that we don't overgeneralize our samples in subsequent studies, for example. Okay. So let's go back to Bayes' rule, and in particular, let's talk about the joint distribution. So this is the numerator of the equation, and this consists of the joint probability of the likelihood and the prior. Now, by itself, the joint distribution does not integrate to 1, and so it's not a probability distribution. This is why we need the denominator, the marginal distribution. This is, again, like I said, referred to as the probability of the data. Another name for it is the evidence. And essentially what the marginal distribution does is that it normalizes that joint distribution so that it can integrate to 1 and become a probability distribution. And that's how we get our posterior probability distribution. Now, this is where we run into issues with Bayesian modeling. So the denominator, that marginal distribution, it can be computed analytically for some simple models, but once we get to more complex models, it becomes really intractable to calculate the marginal distribution. Now, an important aspect of the marginal distribution is that it essentially serves as a constant or a scalar. And it's this observation that really uh, will help us later on when we build our MCMC. And really when we're using Bayesian modeling, just broadly speaking. So let's take our Bayes rule again. So we have our posterior distribution on the left-hand side is equal to the joint distribution divided by the marginal distribution. Now, if the marginal distribution is simply a scalar, it's very functionally a constant, uh, we can actually change the equation just slightly and simplify it. We can actually say that the posterior distribution on the left-hand side is proportional to the joint distribution on the right-hand side. Now, this doesn't get us fully out of the woods yet because we still have to calculate our joint distribution. And as we talked about before, the joint distribution by itself does not integrate to 1. And so now we don't have a probability distribution, and we really can't calculate the probability of our parameter given our data. So this is the problem we've set up. We have our joint distribution at the top, and we need to get to our posterior distribution. And remember, the posterior distribution is proportional to that joint distribution. Because it's proportional, one thing that we can do is that we can sample from the joint distribution some pre-specified number of times, and this allows us to generate a frequency distribution. And if we generalize the frequency distribution as a probability distribution, now we can actually have our posterior distribution that does integrate to 1. And now this is where MCMC becomes particularly important, because now we need to find an algorithm that will allow us to sample from the joint distribution in such a way that it will represent the posterior distribution. And this is where MCMC comes into play. This is how we're going to sample from the joint distribution. Okay, so now we're kind of in the what is MCMC phase. And this is going to be pretty brief because MCMCs, there's a lot of different types of MCMC algorithms. So the longhand form is Markov chain Monte Carlo algorithms. These are just algorithms that allow us to draw samples from a probability distribution. And the samples, the set of samples, that is, from the equilibrium point of the MCMC resemble the target probability distribution. That is, when we draw enough samples from our joint distribution and the MCMC finds its equilibrium point of drawing these samples, that end result is the posterior distribution towards the end. That is, at the very beginning, our samples may not accurately reflect the posterior. And an extremely advantageous aspect of MCMCs is that we can actually sample from them without having to specify the probability distribution. We can actually just sample from an algorithm, and eventually this will, like I said, gravitate towards the posterior distribution, assuming that we obtain an equilibrium point, that is. If we don't, that's another issue altogether. Okay. And now, Today we'll talk about Metropolis Hastings MCMCs. This is considered one of the most quote unquote simple MCMC algorithms out there. It's one of the first, if I believe it is the first MCMC algorithm. And the way this algorithm works is that we're going to generate candidate values of a given parameter using a Gaussian random walk. And we're going to just set a random initial parameter value for the MCMC. This is just to get things going. So as we generate candidate values using this random walk, we're going to decide whether we want to accept that candidate value or retain it, the previous sample that we've drawn. So we can accept our candidate or reject it. When we reject it, we're going to retain the sample that we had before. And then we're going to repeat this until we have our full posterior distribution. And now the steps to the Metropolis Hastings MCMC is, again, we're going to choose an initial value of a parameter. So I'm going to call this theta naught. And again, this is just a random parameter value that is going to help us keep going. Later on, you'll see that I call it theta sub I. Okay. When we get our MCMC algorithm going, step one is we need to propose a new value for the parameter. We'll call this the candidate. So I have it written here, theta star. And then after that, we need to estimate the candidate's acceptance probability. And we'll do this by taking the ratio of the probability of the candidate versus the probability of the previous parameter value. And we're going to calculate these probabilities using Bayes' rule. So you'll see here that I have Bayes' rule, and this is the probability of the candidate value that we just proposed divided by the probability of our previous parameter value, so theta I. We're going to take the ratio of these probabilities, and this is referred to as R, and then we're going to decide whether or not to accept the candidate or reject the candidate. And remember, when we reject the candidate, we accept our prior parameter value, so theta I. And our decision rule for accepting or rejecting the candidate is if the ratio is greater than 1, then we accept the candidate automatically. If we do not accept the candidate, then we actually treat that ratio as a probability of accepting the candidate. So let's talk about this just very briefly. So if the ratio is greater than 1, what does this indicate? This indicates that the probability of the candidate is much higher than the probability of the previous value. And so we do want to accept those parameter values because those are very likely parameter values, at least compared to what we've drawn thus far. And now it might seem weird that if we don't accept the candidate, that why don't we just reject it and simply accept or retain the previous parameter value, so theta I. The problem with not with rejecting it just outright is that we actually won't sample from the tails of our posterior distributions. And so by treating that ratio as a probability and occasionally accepting some of those very low probability candidate values, we can actually fill out our posterior distribution more accurately. Okay. And then finally, we're just going to repeat this steps 1 through 3 over and over and over, n number of times. Okay. So for implementing an MCMC, today I have an example from behavioral economics, because I felt that a relatively real life example that at least I'm familiar with might be helpful for individuals to connect with. So my example, granted it is simulated data, is economic demand for fentanyl among people who have been using fentanyl for some varying number of years. And so economic demand refers to how much an individual will consume or how much they demand a commodity, so in this case fentanyl, across varying prices for that commodity. And there are a few different indices related to economic demand. Here we'll focus on elasticity of demand. Elasticity for fentanyl will be used as an estimate of addiction severity. So elasticity refers to how sensitive consumption is to changes in price. And so if we increase price, we would expect people to consume less of a commodity. But elasticity captures how much less of that commodity are they going to consume. You would expect that if people are highly addicted, let's say to fentanyl, that whenever you increase price, they're still going to consume that drug no matter how costly it is until it's functionally impossible to get the drug, let's just say. And so this is what elasticity captures. And so lower values of elasticity refer to individuals being more addicted. That is, demand is very insensitive to price. Higher values mean that demand is very sensitive to price and that the individual is less addicted. And technically speaking, we'll be working with log transformed elasticities. This is because elasticities are not normally distributed, but when you log transform them, they are. And the primary independent variable will be the number of years using fentanyl. And if y'all are interested in more information about economic demand indices, I do highly recommend this paper by Hirsch and Silberberg that walks through, in particular, elasticity of demand, as well as a metric that they call essential value, which is related to elasticity. And now, when we implement the MCMC, there's going to be a few practical things while you're going through the code. I'm going to illustrate some long form code. That is, these are longer pieces of code that are designed to illustrate what is actually happening in the code a little bit better and to walk through the steps a little bit more. And then I'll actually have a short form of that code that's more concise and that I think performs a little bit better. We're going to program a simple linear regression. So this is going to involve estimating an intercept and a slope. And the way that this will work is that we're going to walk through the steps for the MCMC for each parameter sequentially. So we're going to go through steps 1 through 3 for the intercept, the slope, and then the error term as well. And whenever we calculate these different values, and this will be more apparent in the code, we're going to, whenever we generate samples for a given parameter value, so let's say the intercept, we're going to treat all the other parameters as known. as if we already know that. So when we're generating a sample for the intercept, the the current value of the slope and the uh, sigma will be treated as known values. And then after we generate our candidate value for the intercept, decide whether we accept or reject it, then we're going to move on to the uh, slope, do the exact same thing, but here we'll treat the intercept as a known value based off of the most recently used value of the posterior distribution. And similarly for the sigma, we'll treat that as known, and then we'll generate a estimate for the slope. And we'll just keep doing this for each parameter value. Again, as we walk through the code, I think that this will become a little bit more clear. Okay. And then finally, we'll work in log space. Now, this helps avoid underflow issues. That is, whenever we start working with uh, probabilities, joint probabilities, that is, when we multiply a lot of different probabilities with one another, we start running into issues where R cannot handle the really, really, really small numbers. And so we're going to log those probabilities. And this has the advantage that now we start dealing with larger numbers, but we do need to keep in mind our laws of logs. So for example, when we take the log of a joint probability, this is the same as the sum of those individual logged probabilities. That is, whenever we have log x times y, this is equivalent to log x plus log y. Similarly, whenever we calculate a quotient, so log x divided by y, this is equal to log x minus log y. And again, this is how we'll work with our probabilities as well. Alrighty. Now, that's all I have for the why, what, and how for MCMC. Now, is the time to look through the code and walk through the specific aspects of how to implement the MCMC in R. Alrighty. Thank you all for listening.